Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Today, lecture topic is oxidation state and redox behavior of SBD and F block element. And last class, we have discussed about the periodic table. That the periodic table is divided into four blocks on the basis of electronic configuration. And then we discussed about the periodic trend and we see different properties of the SBD and F block element in the last classes. But today we will focus on the oxidation state and the redox behavior of SBD and F block elements. So the outline of today's lecture is the oxidation state and redox behavior of S block element, oxidation state and redox behavior of P block elements, oxidation states and redox behavior of D block element, and oxidation state and redox behavior of F block element. So first of all, we will discuss about the oxidation state and redox behavior of S block element. So the we can see over here the group uh, first element, and we see that it consists of lithium, sodium, potassium, rubidium, cesium, and francium, and it is called S block element because its electronic configuration involves the ns orbital. For example, the lithium consists of 2s orbital, the rubidium consists of 5s orbital. So all these elements have S electronic configuration, therefore it is called S block element. Similarly, the second group which is included in the S block element is group 2A element, which consists of NS2 electronic configuration. And so on the basis of this electronic configuration, the oxidation state of group A element is +1 while the group 2 element is +2 because they can easily release one electron and form monovalent ion and divalent ion. We can see over here the S block element that the alkali metal group A element consists of Ns1 electron, so it's form a +1 oxidation state and it is called monovalent ion, while the group 2A element consists of 2 electron in an s orbital, so its oxidation state is +2 and it is called divalent ion. The group 1A element form easily +1 oxidation state because its ionization energy is less, and one can easily remove the outermost electron from the outermost shell of the elements, and it can easily form +1 oxidation state. It cannot form the alkali metal, the +2 oxidation state because the second ionization energy is extremely high and making these highly stable due to the high ionization energy. It can form only monovalent ion. The group 2 element of oxidation state is +2. Although the second ionization energy is higher, but as the ns orbital consists of 2 electrons, so when I lose 2 electrons, it's make the most stable compound. So therefore, it show the oxidation state of +2 and it make divalent compound. Now we can discuss about the redox behavior of these S block element. The first A consists of +1 oxidation state, while 2A consists of +2 oxidation state. So as the ionization energy is low, and one can easily remove the outermost electron to make it positive or a monovalent ion or divalent ion. So these S block element, the first A group and first 2A group are strong reducing agent due to the low ionization energy and low electronegativity. These metals readily donate electron, acting as a potent reducing agent. The reactivity trend increasing down the group because the ionization energy is decreases. So as it requires less energy to remove the electron or lost the electron, so therefore the reactivity trend increases and the reducing agent property increases down the group. Now we can discuss some reactions of the S block element. S block element uh, alkali metal and alkaline metal easily react with oxygen to form oxides. So the first A group element, lithium, sodium, and potassium, form M2O oxide because it's have plus one oxidation state and the oxygen has have minus two oxidation state. So when the lithium react with oxygen, it form Li2O. So the lithium have plus one oxidation state, so it consists of two lithium. So it's mean that it consists of plus two lithium and minus two oxygen. And these metal give characteristic color when it burns. For example, one can see over here that the lithium combustion show red flame, the sodium show yellow flame, while the potassium, when it burn, it give a purple flame. So it give characteristic color when it's combined with oxygen and burn. The group 2A element which show oxidation state of plus 2 when it combined with oxygen produce the oxides which have for example magnesium combined with oxygen to produce magnesium oxide MgO. So in this case is magnesium lose two electrons, so it's have oxidation state plus 2 while oxygen have minus 2. So all the group member of second A group form oxide of MO oxides because it's balance the oxidation state of both the elements which are combined. So in this case, we can see over here that the magnesium in the reactant show zero oxidation state, while in the product magnesium have plus two oxidation state. Is it's mean that it lose two electron, so it is a good reducing agent. It's a self-oxidize but reduce the other element, and we can see this behavior, the reducing agent behavior, in the next reaction. Here we can see here the reaction of alkali and alkaline earth metal with water. When these elements react with water, it produces the hydroxide. For example, lithium react with water to produce lithium hydroxide and release the hydrogen gas. Similarly, potassium react with water to produce potassium hydroxide and hydrogen is released. In this case, we can see over here that lithium in the reactant are in zero oxidation state, but in product lithium hydroxide, it show plus one oxidation state. So it's mean that this element oxidize itself, and these are good reducing agent. Similarly, we can see the second A group element, and the alkaline earth metal. When it's react with water, it produce the similar hydroxide ion, but its formula show, for example, magnesium when react with water, it produce MgOH whole 2 because magnesium lose two electrons, so hydroxide ion have minus one charge. So when two hydroxide ion combine with magnesium, it produce magnesium hydroxide ion. So the formula for alkali metal hydroxide and alkaline earth metal hydroxides are different due to its oxidation states. Here we can see the reducing property of S block element. When the S block element alkali metals and alkaline earth metal react with halogen, it produces salt. For example, lithium react with chlorine to produce a lithium chloride. In this case, lithium have the oxidation state in the reactant zero oxidation state, while in product it show oxidation state of plus 2. Chlorine have oxidation state in the reaction 0, while it show oxidation state in the product minus 1. So it's mean that the lithium is oxidized and it reduces the chlorine. So it is a good reducing agent. So all the alkali metals are a good reducing agent. Similarly, the sodium react with chlorine to produce sodium chloride salt. Potassium react with chlorine to produce potassium chloride. Like alkali metal, the alkaline earth metal also react with halogen to produce the corresponding salts. As calcium lose two electron and produce plus two charge divalent ions, get part two chlorine atom combine with it and produce CaCl2. So in this case, in the reactant, calcium have oxidation state of 0, while in the product calcium chloride, it have oxidation state plus 2. So itself it's oxidized and it reduce the chlorine from 0 to -1. So these elements, the alkali metal and alkaline earth metal, are good reducing agent. And the reducing agent property increases down the group due to the low ionization energy. Now the oxidation state of P block element. P block elements show variable oxidation state as we see in the alkali and alkaline earth metal. The S block element, they show fixed oxidation state of +1 and +2, while the P block elements show variable oxidation state. If we see the boron family show +3 oxidation state and +1 oxidation state due to the inner pair effect, and +1 more stable in selenium. Boron show +3 and +1 oxidation state because we can see that the boron have electronic configuration 1s2, 2s2 and 2p1. So the outermost p1 electron, if it lose the p1 electron, it show +1 oxidation state. But if it lose the 2s2 electron and 2p1 electron, then it show +3 oxidation state. So the general oxidation state is +3, and it sometimes show +1 oxidation state. The group 4 element, the carbon family, show also variable oxidation state. And we can see over here that the carbon have electronic configuration 1s2, 2s2 and 2p2. So therefore it show variable oxidation state. It's either lose the 2s2 electron and 2p2 electron to produce +4 oxidation state, or it's only lose 2p2 electron to produce +2 oxidation state. Overall, we can see over here that the p block element show variable oxidation state. Similarly, we can see the other nitrogen family, oxygen family, halogen and noble gases also show various variable oxidation state. Now we see the redox behavior. So across the period, oxidizing character increases while reducing character decreases. So and down the group, oxidizing power decreases while reducing power generally increases. We can see this behavior from the reaction also. When P block element have various reaction, but here I show some of them. The most common one, for example, the P block element carbon family, carbon and sulfur react with oxygen to produce the oxide. For example, carbon react with oxygen to produce carbon dioxide, sulfur dioxide react with oxygen to produce sulfur trioxide. So, if we see the trend in P block element, the electronegativity, ionization energy, and oxidizing power increasing from left to right. And similarly, electronegativity, ionization energy, and oxidizing power increases from top to bottom. Increases from bottom to top. From top to bottom, it decreases. So the oxidizing power increases from left to right, and oxidizing power decreases from top to bottom. Here are some specific reactions of the P block element. For example, boron form trihalide, aluminum react with oxygen and chlorine. When boron react with chlorine, it produces boron trichloride. Aluminum react with oxygen and chlorine, and form with oxygen it forms the aluminum oxide, and with chlorine it forms the aluminum trichloride. Similarly, the carbon and lead is generally unreactive at room temperature, but however, if some catalyst is used and harsh condition is used, then it reacts with various reagents. Group 15 element, specifically nitrogen and phosphorus, they are show some important industrial reactions. For example, nitrogen react with hydrogen to form ammonia, and phosphorus react with sodium hydroxide to produce phosphine. The oxygen family, the oxygen and sulfur form easily the oxide. For example, it reacts with oxygen to produce oxygen form oxide with most of the element. For example, it reacts with various metal to produce metal oxides. Similarly, sulfur reacts with oxygen to produce the sulfur oxides. So it's react with various elements to produce the oxides. Group 17 elements are highly reactive and forming hydrogen halide. For example, chlorine react with hydrogen to produce hydrogen chloride, react with fluorine react with hydrogen to produce hydrogen fluoride. So all the halogen react with hydrogen to produce the hydrogen halides, and they are strong acids. The group 18 element noble gases are mostly unreactive. However, some heavier gases such as krypton and xenon from fluoride and oxides. So now we can discuss about the oxidation state of D block element. An oxidation state of D block element is variable like the P block element, and it shows various oxidation state from +1 to +8, and one can see over here the oxidation state of scandium that it show only +3 oxidation state, while the titanium, vanadium, chromium, and all the other D block element show various oxidation state. And this variable oxidation state is due to the small difference between their ns orbital and n minus 1 d orbital. They have very little energy gap, so it can easily lose the inner orbital electron also, so it show variable oxidation state. Similarly, as we discussed about some of the reactions of the P block element and S block element, we can see over here some of the reaction of the D block element. And specifically, we discussed the redox behavior. So the D block elements are good oxidizing agent. We see that the S block elements are good reducing agent, while the D block elements are good oxidizing agent. For example, we can see over here the manganese. It shows oxidation state from -3 to +7, and chromium from -2 to +7. So they are good oxidizing agent. It's itself reduce and oxidize the other element. So these are the good oxidizing agent. One of the most important and strong oxidizing agent of the D block element are potassium dichromate and potassium permanganate. The second important reaction behind the redox behavior is the complex formation, where the d block element, due to the vacant d orbital, it's coordinate with various ligand and produce various types of complexes, as we can see over here, the iron thiocyanide complexes and copper complexes. So all the complex formation, all the complexes which are formed are colored. Some other reaction of the D block element is the catalytic activity that various transition metals such as vanadium pentoxide, iron, and nickel, they are good catalyst. As you have studied in the FSC or maybe in the first semester, the hydrogenation reaction, that hydrogenation reaction is catalyzed by the nickel powder. So the D block elements are also good catalyst. There are some other reactions of the D block element, such as they react with an acid, and with acid, they react with non-oxidizing acid to release hydrogen gas, though many are less reactive than alkali metals. Um, Oxygen, they react with oxygen to form diverse oxide, such as chromium react with oxygen to produce chromium oxide, vanadium react with oxygen to produce vanadium oxide, and manganese react with oxygen to produce manganese oxide. They also react with halogens. For example, iron react with chlorine to produce iron chloride, copper react with chlorine to produce copper chloride, zinc react with chlorine, bromine to produce zinc chloride or zinc bromide. So the D block elements have variable oxidation state, and they are good catalysts, and they react with halogen, oxygen, and various acids, and they produce various types of colored complexes. Now we have discussed about the F block element. The oxidation state of F block element is also variable oxidation, show variable oxidation state +3 to +7. However, they have the general oxidation state of +3. However, due to the small energy difference between the 5f and 6d orbital, they show variable oxidation state. The lanthanide stability is linked to the f orbital if it is empty, are full filled or half filled. They are also stable, so therefore it show variable oxidation state. If we look the reaction of the A block element react with easily with oxygen to produce the oxide. For example, lanthanides react with oxygen to produce the lanthanide oxide. Similarly, with non-metal, it readily react with non-metals such as halogen to form halide. For example, lanthanides react with chlorine to produce lanthanide chloride. Similarly, react with sulfur to form sulfide and with nitrogen to form nitride. They also react with acid and it dissolve the acid and release hydrogen gas. So these are all about the redox behavior and oxidation state of the S, P, D, and F block element. Thank you.